Welcome to this lecture number 2 of this module 1, Introduction to Computational Hydraulics, and this unit is about problem definition and governing equations. So, what are the learning objectives? To identify governing equations for hydraulic systems. So, in this particular lecture, we will try to identify the governing equations related to hydraulic systems. Introduction. Governing equation defines the relationship between variables in terms of ordinary differential equations or partial differential equations, and it relates the independent and dependent variables. ODEs or PDEs represent conservation laws, that is mass, momentum and energy in general or simplified form. Depending on the nature of the problem, we can use a 3-dimensional form or a simplified 1-dimensional equation for the problem. So, what is this ODE? ODE is a differential equation with one independent variable. And what is this PDE? PDE is differential equation with 2 or more independent variables. Now, what are the basic principles? Basic principles are conservation of mass, conservation of momentum and conservation of energy. If we talk about this conservation equation in general, so for incompressible fluid flow, we can write down the differential equation or partial differential equation like this. In this case, del u by del x represents the change in the x direction, and del u by del y change in the y, and del u by del z change in the z direction. U, v and w, these are 3 components of the velocity vector in 3 directions. And what is this momentum conservation equation? In x direction, we can write the momentum conservation equation. This is your temporal term, this is your advective term, and this is your pressure term, and this is the body force or gravity term, and this is our diffusion term, where mu is the dynamic viscosity, rho is density of fluid, p is pressure, and we already know that u, v, w are the components of velocity. Now, in our previous lecture, we have seen that if we perform this experiment of 2 density fluids, that is lock exchange flow. So, from experiments we can simulate or we can get information about the system, and from numerical case we can simulate the corresponding variation with the help of computers. So, to solve this problem, we need to solve our conservation of mass and conservation of momentum equations. So, if we talk about groundwater movement in aquifers, then we need to define the conservation of mass, that is depth integrated mass conservation equation for groundwater flow, where S is our storativity term, for unconfined aquifer it is specific yield, for confined aquifers it is storage coefficient. Interestingly, this Q is Darcy discharge and F is source or sink term. So, change in head or groundwater head can be represented using this mass conservation equation. Now, if we talk about momentum equation in case of aquifer or aquifer flow thing, then Darcy's law is the momentum conservation equation, where Q is the Darcy velocity or Darcy discharge vector, and T is the transmissivity, K is hydraulic conductivity, and as we can see that this T is calculated as minimum value of H and ZU. ZU is the top aquifer elevation minus the bottom aquifer elevation. That means the saturated thickness portion. So, if we talk about the one dimensional flow in terms of ordinary differential equation, by neglecting the transient term and the variation in y direction, we can write it as del qx dqx by dx equals to f, and momentum conservation equation can be written as qx is equal to minus t del dh by dx. So, similarly for contaminant transport, we need to solve one hydraulic head related equation, that is the mass conservation equation. Kxx, Kyy, these two are our hydraulic conductivity values in x and y direction. H is the potentiometric head, Qs is the volumetric flux per unit volume, Ss is the specific storage, and this thing is applicable for confined aquifer system. We need to solve another extra equation for contaminant transport, that is our scalar transport equation, where C is the concentration and eta is the effective porosity, dx dy dxx dyy are the hydraulic dispersion coefficients along x and y direction, and dxy dyx, these two are the hydraulic dispersion coefficients along cross direction. Vx and vy, these two are velocity along x and y axis. These two values can be calculated from Darcy velocity. If we talk about channel networks, similarly we need to define two equations, one is for conservation and another for momentum, mass conservation and momentum conservation. If we talk about the mass conservation equation, in that one this del H by del T that considers the change in the channel water depth with time, 1 by B, B is the free surface width, del Q by del X is the change with respect to x direction. That means, it is one dimensional in space and time, both are considered. Momentum conservation equation, this equation we can relate the change in Q with respect to time with other variable, that is h, and SF and S naught, these two are actually friction slope and bed slopes. SF can be calculated from Manning's equation, and A is the cross sectional area. If you consider surface flooding, the equation is simple. We need to solve this A del H by del T into Q. Del H by del T considers the change in depth with respect to time into area, that is actually net inflow of water to the plot. So, we should consider all kinds of inflow conditions. It can be inflow from the canal section or rainfall to the surface area. So, A is the cross sectional area of the plot. So, if we can discretize this, we can solve the surface flooding problem. If we consider this open channel flow, that is hydraulic jump, U and W, these two are actually longitudinal and vertical velocity components. So, for this one, to solve the hydraulic jump, we need to consider mass conservation. This is actually vector form of our previous mass conservation equation, considering all directions, but in this case only longitudinal and vertical components will be there. And momentum conservation equation, it is written in terms of total derivative du by dt, or total derivative of u, that actually considers the advective term plus temporal change in the velocity, and tau by rho, that is sub particle scale tensor, and nu is our kinematic viscosity, and g is acceleration due to gravity. So, depending on a equation and direction, we need to assign different values. If you talk about pressurized conduits, we should have equation for H and Q. So, depth integrated mass conservation equation for surface flow can be written in terms of temporal change in the piezometric head, and this is change in the discharge, where C is the wave speed, Q is the discharge, T is time, and A again cross sectional area. And if we consider the momentum, so momentum is again the change of discharge with respect to time and change in H with respect to x direction. So, we are basically considering one dimensional flow system. In this case, J's and Ju, these two are separately defined, and J's actually that is steady friction loss, and unsteady friction loss is the Ju. We will discuss these equations in individual units during solution process. So, if we consider pressurized conduits and in network system, then we need to solve again mass conservation equation that is represented by this particular equation, where Q is flow along line J and P is pressure along line J, area is represented by Aj, rho is density, tau J, this is another term which is represented, this cross sectional area for the pipe is J, and Lj is the length of pipe, and this capital lambda is the set of fluid lines. So, momentum conservation equation, again it is for change in P with respect to time, and other term is related to Q, and tau J is the cross sectional frictional resistance, and lambda Lj, these terms are defined like our previous mass conservation equation. Now, if we consider surface water groundwater equation, and in depth average sense, if you want to use those equations, so we can write this mass conservation equation for surface water height, that is represented in terms of this equation. This is Ps, again Ps, this is actually depth averaged velocity into depth, and C is a Chase's coefficient. This is our momentum equation, it represents the variation of Ps, beta is the momentum correction factor, and this is our usual term, and G is acceleration due to gravity in this case. So, for groundwater we need to introduce this eta or effective porosity term to consider the porous medium. Similarly, for momentum conservation we need to use Darcy's law. So, we can combine these equations with channel flow to solve this surface water groundwater interaction problem. If we consider regional scale modeling, then for channel flow we need to solve this relatively general equation where QL is the lateral inflow or outflow, ML is the lateral momentum flux, and A naught is the dead storage in channels. So, with this two equations, if we compare these two, this QL and ML relates it with the groundwater equation. So, we can consider a datum, and from this datum we can take this Hg, which is groundwater level, Hr is the river level, and Zr the bed level, and Zb is the height of our impervious layer. So, with these variables we can define our mass conservation equation, combining our Darcy's law. We can write it, and in this case as Zb is the height of our height of impervious layer. So, we are considering the flow over this impervious layer only. So, that is why this Hg minus Zb term is there, and I is sourcing term that is added, and Sy is the specific yield for the unconfined aquifer system. And finally, if we talk about this 1D 2D integrated system, where we need to consider the channel water depth, channel discharge, surface flooding depth or depth of surface water, along with velocity components in x1 y directions, we can express it in terms of this vector form, where U1D, 1D is for channel flow approximation, A and Q, these two are for one mass, another one is momentum equation. F1D, again this Q is for mass, Q square A, and Gi1, this is for momentum equation. H1D, again QL, which is which considers the lateral discharge, is for mass, and this one is for momentum equation. In combined form or short form, we can write this governing equation, and this comma t represents the derivative with respect to t, and comma x, this is actually derivative with respect to x. So, in our previous equation, I1 and I2, these two are actually general terms and defined for general cross section like this, where H is the depth of flow, and I2 and I1 are calculated like this. If we consider the two dimensional mass and momentum conservation equation, then again we need to calculate the things U2D. The first one is for a mass conservation and momentum conservation in U direction. HV is momentum conservation for V direction. Like this, H or first row represents the mass conservation equation, second and third these two are for momentum conservation in or x and y directions. So, what is this IR? IR is the rainfall, and finally, we can write it in terms of vector form. So, with this governing equations, we can conceptualize our system in terms of 1D or 2D or 3D equations, in terms of 1D, 2D or 3D equations. Thank you.